let's suppose that f is a function on three-dimensional domain in three-dimensional space. So let's suppose that f is a function with continuous second partial derivatives. All right, what we'd like to do in this video is compute the curl of the gradient of this function here. So let's compute. All right, the curl of the gradient of this function f. So let's start by remembering what the gradient of this function is. The gradient of a function is a vector field. So we start off with just a function defined on some domain. All right, we can draw the domain. The domain is some blob here, let's say E. F is a function which assigns to this a real number. All right, and the gradient vector of this, or vector field of this function assigns a vector to every point back here in the domain. Okay, so gradient f lives over here in the domain space E, and this gradient vector field is given by partial of f dx in the first component, partial of f dy in the second component, partial of f dz in the third component. Okay, in the z component. And what we would like to do now is compute the curl of this vector field. So remember, the curl is an operator that acts on vector fields and gives back vector fields. Okay, so it takes in a vector field and it outputs a vector field. So let's do it. Remember, the curl of any vector field, I'll just write our vector field here, gradient f. This is going to be the del operator crossed with that vector field. So in your mind, when you write down the definition here, this is the vector field input, right? And for us, that vector field is just the gradient vector field of our function lowercase f. And so when we take a curl, we remember that we can arrange this into a matrix for like a systematic method of computing this. And what we have to do then is compute the cross product with this symbolic vector operator whose components are d by dx, d by dy. It's just the partial derivatives, right? The operator del is just if you were to delete f up here from all the different spots. If you delete f from everywhere, you'd get this vector del, and it's exactly this, except I wrote down dx instead of dz in the third component. And then in the next line, we have to write down the gradient of f. Well, that's the same looking symbol, right? Except now the f's are in there. So now it's df by dx, and these are functions, okay? df dx, df dy, and df dz. Those are functions because the del operator has already been applied to f. So each of these are functions. Now, we need to compute. How do we compute? The cross product we always compute the same way. We go across, especially when it's symbolic like this, right? We go across the top row and we write out the component functions, okay? And as we go across, we delete the row and the column that I lives in, and we apply the operator in row 2 to the function in row 3, and we have this kind of addition-subtraction relationship, right? So for the I component, we take dy, d by dy, of df dz minus, the other direction is d by dz minus df dy. Times, I'm sorry. So d, not times, of. This is an operator. d by dz of df dy. All right, so you have to be careful here. I was getting carried away. The next component, the j component, I'm going to add it. But remember, if you add the j component, you have to then reverse your thinking. And the component in the j slot is then d by dz applied to df dx minus d by dx applied to df dz. All right, and then finally, in the k component, we have, this goes back in this usual order, so d by dx applied to df dy minus d by dy applied to df dx. All right, and we want to work these out. You've probably already noticed that these things are looking pretty similar to each other in each component slot, but let's write out exactly what we have. And I'm going to put this back in vector form. I tend to like vector form. By vector form, I mean the angle bracket form. I tend to like this a little bit more. The physicists, engineers, other areas of math like the IJK, and sometimes it's useful for me as well, but I tend to go with the one that that requires the least writing. So remember, this is the curl of our gradient field. And when we work this out, we end up with the second derivative of f dy dz minus the second derivative of f dz dy. That's the first component. Okay, and all the other components are going to look very similar. So as I write these down, you think about the reason, or think about what we can do when we see this, the mixed second partial derivatives. So second derivative df d squared f dz dx minus second derivative dx dz in the second component, and then the third component is the dx dy minus d squared f dy dx. All right, so what'd you come up with? Well, remember at the very beginning we assumed that our function had continuous second partial derivatives, and now down here we've got a statement with the differences of the mixed partials, right? And so because our function is assumed to have continuous second partial derivative, then Clairaut's theorem applies, right? And remember, Clairaut's theorem tells us that the second derivative, all the mixed second derivatives here, so d box, d triangle, all right, okay, triangle's a bad one because triangle is one of our symbols here, right? So d box, d diamond, right? These are just placeholders, so this is me being wacky. But d diamond, d box, these are equal, right? Clairaut's theorem says that these are equal as long as the function, these partial derivative functions, the second partial derivative functions, are continuous. All right, and that was our assumption. Since these are equal, what does that tell us? Well, it tells us that this difference must be 0. Same thing here. This difference must be 0. And finally, this difference must be 0. Okay, and so what we end up with is that in this scenario, the curl of a gradient, and in this scenario is just that the function has to have continuous second partial derivatives. And in that scenario, the curl of a gradient is always equal to 0, 0, 0, but this is a vector, right? So it's equal to the 0 vector. And so what we end up with is this theorem. All right, and it says the following. If f is differentiable and has continuous, so to have this property, it has to be differentiable, but has continuous second order partial derivatives on a domain, so let's just say partial derivatives on a domain D, or E I guess we called it, then the curl of its gradient field is always equal to the 0 vector field. Okay?